An electron enters a field with a velocity of something in the direction of the field. How far does the electron travel before being stopped? So let's pretend we have a magnetic field. Oh, so this should say electric. I keep making that mistake. Electric field. So let's say the electric field is in this direction, because it's saying the electron enters the field. So let's say it suddenly enters the field, and it's moving in the same direction as the field, right? So this is our initial velocity, right? It's like it's got this big velocity, 3 times 10 to the 4 meters per second, moving very fast in that direction. How far does the electron travel in the field before being stopped? Well, you might be tempted to say, what do you mean being stopped? It's going in the same direction as the field. It isn't going to push it that direction. But remember, electrons are negatively charged. They want to move against the field. So even if it's moving to the left, it's going to be slowed down by the field, and eventually it's going to stop, right? So we can look at two things here. We can look at two locations. We can look at when the electron enters the field. We'll call this location 1. And then a little while later, it's going to be stopped, right? That same electron, it's going to slow down, because there's like a force going in the opposite direction. In fact, if we drew a little free body diagram of that electron, right? Just I'm going to do this off to the side. We did a free body diagram of that electron. The force is going to be pointing to the right, right? And we can figure out the magnitude of that force if we wanted to. But basically, we have 2 points. We have when it enters the field and when it stops. Those are going to be the 2 critical points for us here. And hopefully your brain is already starting to work with how we've done questions similar to this with gravitational fields. You have something moving at a speed. It's eventually going to stop. What can we use? There's actually more than one way to do this question. You could do it with kinematics, but I think the easiest way to do this is with energy. Because at location 1, we know this electron is going to have kinetic energy, right? It's moving at a high speed. But it's not going to have any electrical potential energy, because it hasn't entered the field yet, or it's just entered the field. It hasn't gone anywhere in the field. But as it's moving through that field, it's going to start losing electric potential energy, or gaining electric potential energy if you want to look at it that way, right? It's going to basically come up with resistance. It's like it's going uphill, right? And at that point too, all that kinetic energy has disappeared. But what we're left with is electric potential energy, right? Now, the formula for electric potential energy has distance in it, so we should be able to use that. So the key here is at the beginning, at point 1, our electrical energy is 0, our kinetic energy is some value, which we can calculate, and at the end, it gets swapped. So what we can basically say is that our electrical energy at the end and the kinetic energy at the beginning are going to be equal to each other. So EK equals EE, right? And we have an equation for each one of these. So our kinetic energy is 1/2 mv squared, and our electric potential energy is equal to, epsilon q delta d, right? We're trying to solve for delta d. We want to know how far it travels before stopping, right? So this is essentially what we're trying to find. And we know the charge of an electron, or we can find the charge of an electron. We know the mass of an electron. We know the speed it's traveling at, and we know the field strength. So this just becomes an exercise in calculating, plugging stuff in and calculating that. So pause the video here, do the calculation yourself, and I will reveal the final answer when you're done. So the answer, I believe, is our delta D is 0.0045 meters, which is about 4 or 5 millimeters, right? Sounds like a tiny amount, but remember, an electron is very, very, very light. Even though it's moving fast, it has very low mass, so it's very easy to slow it down and stop it. So it makes sense that it's a small number, and that the electron is basically stopped in about 4 to 5 millimeters. So in this last question, we have a proton that's launched through 2 plates with a high rate of speed. So our proton, our positive particle, is going to be launched this way. And we know a few things about these plates. We know the voltage difference between them. So we know our delta V, not delta V as in change of velocity, but our electric potential difference is 500 volts. We also know that they are 15 millimeters apart. So our delta D is 15 millimeters, right? So we want to draw, all we're asked to do in this question is draw a free body diagram of the proton while it's between the plates. So what we need to do, we need to find, the forces acting on it. And remember, the force acting on a charge, we can calculate using Coulomb's law, or the simplified version of Coulomb's law when we know the field strength. So we would say the electric force acting on a proton or on a charged particle is going to be epsilon, which is the field strength, times the charge, right? We know the charge of a proton, so that's not the problem. We can look it up. But we need to know the field strength, right? That's the thing we need to figure out. Now, we're not given the field strength. We're given the electric potential difference. So in order to find the field, basically we need to find the field strength. To do that, remember, there's a relationship between our electric potential difference and our electric potential energy, which relates the two in terms of the field strength, because the field strength is in our electric potential energy. It's not in our electric potential, but when we combine them in this question over here, we said that V is equal to epsilon delta D, right? So that's a very handy relationship, that the field strength, or the voltage, the electric potential, is equal to epsilon delta D, right? And what that tells us again is that the electric potential difference between any 2 points in a field is going to be something based on the field strength and the distance between those 2 points. So if we know the electric potential difference between the two plates and we know the distance between the two plates, we can easily calculate the field strength, right? The field strength in this case is just going to be the electric potential over the distance between them. So it's just going to be 500 volts over 15 millimeters. Now again, we need to be careful, put that in meters, 0.15 meters. And we get the field strength is 500 divided by 0.015. It's a huge number, well, not that big, but 33,333. So let's just carry all those significant digits for now. And that again is newtons per coulomb, right? That's our field strength. Okay, and the next question is, what direction is that field? Well, we know the field is always going to go from positive to negative, right? It's like the direction that a proton would go in that field. So now that we have the field strength, we can figure out the force, right? Because we have this relationship right here, right? So the force, the electric force on that proton is going to be the field strength times the charge. Feel free to do the calculation yourself. For the sake of time, I'll just show you what the answer is here. It's 5.33 times 10 to the negative 15 newtons of force. So it's a tiny amount of force. And then we need to create our free body diagram. So I'm just going to do that off to the side here. Here's our proton. What direction is this force going to be applied? Well, remember, the whole point of an electric field is the field lines is that the field lines show the direction of force applied to a charge. So because this is a positive charge, the force is going to be applied in the direction of that charge, right? So, in the direction of that field. So because the field's going down and because it's a positive charge, it's going to be pushed downwards. And you can think of it, it's attracted to this negative plate right here, right? So that's going to be the force. And the force is just going to be 5.33 times 10 to the negative 15 newtons. Are there any other forces acting on this charge? Well, you might say it has a high speed. It's being launched into this field at a high speed. So it must have a forward force, right? Well, no, remember, it's just moving at a constant speed. I never said that it's like accelerating in that direction or anything. It's just moving at a constant speed in that direction, which means there's no forces acting on it in that direction. The only force that's acting on it is this downwards force. So if you think about it, what's going to happen as this proton moves through the field? Well, it's going to move very fast horizontally, but it's also going to be attracted to this bottom plate down here. So what it should do is it should actually, as it's moving horizontally, it should curve downwards. Right? You see that? It'll curve downwards. And you could actually calculate the acceleration of it in that direction now that we know the force. I'll save that for another problem though. The last thing that I want you to take note of is that this is what would happen to a proton in this case. You have to be careful. If it's an electron in this case, remember the electron wants to go against the field. The direction of the force is going to be in the opposite. So if this was an electron that was launched in here, it would try to bend upwards, right? It would have the same sort of idea, but it would sort of try to bend upwards, right? Okay, there you go.